Hi folks! Today we're looking at transformations of logarithmic functions. So basically we're taking basic log graphs and we're messing with them in some way. So just to recap, our standard log graph, if we have log base c of x, where c is, let's say c is greater than 1, because that'll be the most common case. Definitely needs to be positive. Here's the look of the function. It looks like this. And it passes through the point 1, 0, and also the point c1, because the log base c of c would just be 1. We also have a vertical asymptote, and that is going to be at the y-axis of the y-axis, and that has an equation. Okay, the y-axis has the equation x equals 0. So just as a recap of our basic function transformation techniques, if we transform some point xy on some function like this, the a provides us our vertical stretch factor, so that's going to be multiplied by y. 1 over b is our horizontal stretch factor, so we have 1 over b times the x value. And then we're going to be shifting, and we're going to be lifting. The most important feature of a log graph is probably its asymptote, and that is controlled by the horizontal shift, or the h value. So let's do a few sketches. We'll do some basic ones to start with. I've got y equals log of x. So again, if you don't see a base, the base is assumed to be 10. If I go and sketch this, I have a point of 1, 0, and also of c1, where c is the base. Hold on now, we know the base in this case. The base is 10, so let's write that in. 10, 1. There we go. So there are 2 points that I know. I'm going to just label this as 10. And then to make the graph, it has to be a smooth, kind of banana-shaped thing that is going through those 2 points. That's a pretty good graph of y equals log x. Let's try the next one, y equals 2 log of x. So one way that we can think about this is through transformations. This has a vertical stretch, x2, or by a factor of 2. As a map, that would mean that we would take our points and nothing would happen to the x, and the y would be multiplied by 2. Now think about the key points on the basic graph. Usually they're 1, 0. That's on every logarithmic graph. Let's look up here. Any logarithmic graph, we have 1, 0. We also have c1, where c is the base. So that'll be 10, 1 for us. Let's see what happens to these points. Here we'll get 1 is 1, and then 2 times 0 would be 0. In the next one, nothing happens to the x. The y gets multiplied by 2. That's the look of our function. Now let's make a graph. So again, I have 1, 0. And somewhere out here, I have 10, 2. Okay. So this one's just been stretched up, and we'll just connect them up. Still has that vertical asymptote. So the only difference between the first one, which we might call A here, and the second one, B, is that it's twice as tall. And some of you will be able to do that without mapping, but of course when things get rough, we may want to map. Here's another important one. We've got log of x minus 2, so again, the base is assumed to be 10. This one is going right 2. Alright, so as a map, if I wanted to map it, I'm just adding 2 to my x values. The key points on a basic log base 10 graph would be 1, 0, and they'd also be 10, 1, because 10's the base. So 1 plus 2 makes 3, and the y stays the same. The next one, we'd have 10 plus 2 makes 12, and the y stays the same. Now we're going to graph this. So let's see. Right here at 3, 0, we've got a point. And at 4, 5, 6, 7, 8, 9, 10, 11, 12. Right here at 12, 1, we've got another point. 12, 1. Okay, and 3, 0. The thing that I didn't do is write in the asymptote, and I really should have done that probably first thing. As soon as I see a right 2, move the asymptote. And the asymptote used to be on the y-axis. Now it's going to be 2 to the right, so it's going to be this line here, which is x equals 2. Now I have everything to be able to draw the graph of this function. So I'll just connect these points as smoothly as I can, and make sure that they hook around the asymptote. We'll do 3 more of these log base 10 graphs. Some of them I think you can probably just do by inspection, by looking at it. So this one here, we'll call it D. It's got an x-axis reflection. So some people are going to be able to just look at this and go, oh, well, now it looks like this, and that point that was at 10(1) is now at 10(-1). If I just compare it to the basic log x graph up here. For the rest of us, we may want to map it. So I'll go through mapping this one. Okay. An x-axis reflection means that we change our y values. If you flip through the x-axis, you're making your y as negative. Usually a log graph has the point 1, 0. It always has 1, 0. And it'll have C1, where C is the base. So let's see. 1 and -0, that's still just 0. Here we'll have 10 and -1. Nothing has happened in terms of horizontal stretches or shifts, so nothing has happened to our asymptote. And it's actually only the shift that would affect our asymptote. So we've got the point 1, 0. I label it. I'm going to have the point over here, 10, -1. And then I just connect as smoothly as I can, making this asymptotic banana shape. Now, some people will think that looks like an exponential, but this actually continues down forever. The main thing here is that it has a y-axis asymptote. All right, next one. We got a negative in front of the x. That's a y-axis reflection. So again, some people are going to be able to do this by inspection. If not, then we'll go to the map. So y-axis reflection means that the x turns negative, and I'll just apply that to the key points, 1, 0, and 10, 1. Let's see what happens. I'll get -1, 0, and I'll get -10, 1. Let me make that graph. I can already think here, it looks like it should be going to the left instead of to the right because of the y-axis reflection. So it's going to have a point here of -1, 0, and a point up here of -10, 1. Let's just connect that all together. And again, give it that y-axis asymptote. I'm trying to make them as smooth as possible, but it's kind of tricky on the iPad. All right, one last one. Log of 2x. So here we have a horizontal stretch, because it's right in front of the x. And it is by a factor of the reciprocal, by a factor of 1/2. So as a mapping rule, that means the x's are half as big. If I stretch it horizontally by a factor of half, I'm making it half as wide. And I just apply that to my key points. Okay. And the reason that I'm using 10, 1, again, is because the assumed base, if there is no base, is going to be 10. All right, let's plug these in. Half times 1 is just a half, 0. The next one, we'd have half times 10, that's 5, and 1. Now I can go ahead and sketch this graph. Maybe I'll zoom in to try and do a better job. Okay, so here's 1, 2, 3, 4, 5. Here's going to be 1. 5, 1's easy to plot. 5, 1. And then this will be the point over here, a half, 0. And now I'm just going to connect these up. Nothing has happened with the asymptote, so it's still on the y-axis. And there we go. So there are a bunch of graphs of log base 10, but the technique of using the mapping and the key points is going to help us out here, unlike the exponentials where we just made a table of values. We're going to try a couple that are a little more involved, and then there'll be some practice time. All right, now things are looking pretty serious. We've got log base 3 of a half by x minus 1 plus 3. So let's just catalog all the things that are happening here. First of all, the base is 3. So our key points whenever we map are going to be 1, 0, and 3, 1. They're going to get transformed somehow. The question is how. And to do that, we need to catalog our transformations. So right here, we have this half. That is horizontal stretch by a factor of 2. And our other key features here are moving right 1 and up 3. Right 1, up 3. Now, the most important of these is the right 1. It is telling us what's happening with our asymptote. Asymptote. So honestly, if I were going to graph this, I might, right at this point, make my grid, but immediately put in that asymptote that has moved 1 to the right. From here, I want to build a map. So we're going to the right 1. That would be x plus 1. We also have a horizontal stretch by a factor of 2. So that'll multiply our x's by a factor of 2. So 2 times x. And then right 1. Then we're going to go up 3. That affects our y's. And we're just going to apply this to a bunch of points. So 1, 0 becomes 2 times 1 plus 1, or 3. And then 0 plus 3 becomes 3. Similarly, for the point 3, 1, let's see what will happen. I'll have 2 times 3 plus 1, that's 7. And if you want to see how we got there, maybe I should show the process. I'm putting in a 3. So looking at this map up here, this would be 2 times 3 plus 1. And then the y's are going to be y plus 3, so 1 plus 3. Now I can work all those out. 2 times 3 plus 1 is 7. 1 plus 3 is 4. So let's actually just write in the numbers. 7, 4. There are a few points. Are they the only points on this graph? No. Could you have used different ones? Absolutely. Are they fairly easy ones to generate without a calculator? I think that they are. So the point 3, 3 is here, and the point 4, 5, 6, 7. 7, 4 is here. And now I can just connect up. I don't know exactly where the x-intercept is. It's probably not right on 1. But I have 2 key points, so that's pretty good. If you wanted to talk about the domain of this function, the domain would be x is greater than 1, okay, because you can just look at it and see all the x's are greater than 1. The range is all real numbers. It does go up and down forever. There is no horizontal asymptote. So that's the basic technique for graphing even the most brutal of log functions. 2 points and an asymptote will do it, and probably mapping helps you find those points. Let's take a look at the next one. We'd have a 3 here, so that's going to be a vertical stretch by a factor of 3. We have a negative here in front of the x, so that is a y-axis reflection. And this is all from Chapter 1, or transformations of functions, for interpreting these. It's also got an x plus 2, so that's left 2. Let's build a map. So, vertical stretch by a factor of 3, that affects your y's. You're going to get 3y. Y-axis reflection actually turns your x negative. And then we go left 2, so x minus 2, and that x is negative. Just so I don't miss it, I would probably start by actually graphing that asymptote, which is given by this horizontal movement. So let me make a little grid here. It's gone left 2. Great. There's my asymptote. That's what everything is going to kind of hook around. And now I just need to find out what's going on with the point 1, 0 and C1, where C is the base. So C is 2 in this case, so the base is 2. And I just plug in. Negative 1 minus 2 is negative 3. 3 times 0 is 0. Next one. Negative 2 minus 2 is negative 4. and then 3 times 1 is 3. Now I have a few points. Let me plot them. Okay, there's negative 3, 0. Here's negative 4, 3. There are 2 points. And then we just connect them up. And we're not really surprised that it's going to the left because it had a y-axis reflection. If you have a different way of generating these graphs, that's fine. Just make sure that it's a technique that you can do without a calculator. So if you like to actually put in numbers and make a table of values, that works out great as long as you pick convenient numbers. Now that we've generated a few, I think what we want to do next is take a look at the steps for graphing a log function. So in my mind, it would be these 3. Determine the transformations, make a mapping rule and apply it to the points 1, 0, and C1, where C is the base of the log. Plot your points and move your asymptote if necessary. And that comes from the horizontal shift. I would actually move your asymptote before plotting the points, just to make sure you don't forget. So we have some practice questions that you can graph. These are also in the link down below that you can find them. So why don't you pause the video and give those a go. And you can find the answers also down below, or in 5 seconds I'll put them up on the screen. And here we go. Here are the answers. The domains are given in red there, and they're just coming from looking at where that asymptote is. Sometimes actually generating the graph is kind of overkill for these questions. Sometimes you just need to know the direction it's opening and what its domain is. So we're going to look at some log function properties without graphing. And I'm just going to hark back to the very first lesson we had, and we talked about domain. And there are basically 3 illegal operations. You can't divide by 0. So if you have 1 over something, I'm going to use my favorite variable of a poorly drawn unicorn, that unicorn, or whatever that expression is, can't be 0. You can't take even roots of negatives. So if you have the square root of something, then that something has to be 0 or positive. So it has to be greater than or equal to 0. And the final thing that's illegal is logs of negatives and 0. You can't take the log of negative, you can't take the log of 0. So that leads to a domain restriction, something like this. If you had y equals log base c of something, anything at all, that thing that we're taking the log of has to be positive. So let's put that to use down here. We're saying without graphing, find the domain, the equation of the asymptote, and the x-intercepts of these 2 functions. One of them's pretty easy to graph, one of them's a little more painful. So let's check this out. We have log base 3 of x minus 3. What I know for sure is that x minus 3 has to be positive. I can't put in negative numbers. So you could mess around and find the lowest number you can put in. Like you obviously can't put in a 0, because that would cause you to take the log of negative 3, which is not a thing. You might see by inspection the lowest number that we can put in. Or you might just go ahead and say the domain is going to come from taking whatever we're taking the log of and saying that has to be positive. So x minus 3 has to be positive, which means that x has to be greater than 3. There's our domain. And it's true. If you put in any number bigger than 3, then you'll be able to find the log. So if I put in 4, I'd have log base 3 of 4 minus 3, or 1. That's the thing. The equation of the asymptote. That's just going to be the boundary of the domain. And if I actually did a rough sketch of this, it's going to be something that's moved to 3 to the right, and it's going to go up like this. Okay, there's a rough sketch of this one. So right on the boundary of the domain, you have the asymptote. That would be x equals 3. It comes from this number over here. Domain is x greater than 3. The asymptote is x equals 3. I'll write that in there, that this is the asymptote. And the equation of the asymptote is not asymptote equals 3, it's x equals 3, and that's because it is a vertical line. Okay. Lastly, the x-intercept. So to find any x-intercept, we sub 0 for y. And in this one, it'll work out pretty nicely. In the next one, it may not. But we've got this equation up here, y equals log base 3 of x minus 3. If I put in 0 for y, I'm going to have 0 equals log base 3 of x minus 3. And at this point, you might say, okay, I don't know what that number is, but we can convert it to exponential form. Now, maybe I'll just rewrite it with the log on the left-hand side so that I can think of this as bay. So now I know 3 to the 0 equals x minus 3. Let's continue that. We have 1 equals x minus 3, or x equals 4. Maybe I'll write that the other way around. That's our x-intercept. So if I were to graph this nicely, I'd now know this is at 4, 0, which I also could have found by using mapping. If you are going to graph anyways, this is all probably overkill because you'd rather simply make the graph with mapping. Let's take a look at the same stuff for this one. So we've got log of something or other. For the domain, that something has to be greater than 0. So 2x plus 5 has to be greater than 0. The negative 2 out front and the 1, they don't make a difference. They are vertical transformations. They don't affect the domain. So we'd have 2x is greater than negative 5, or x is greater than negative 5 over 2. And some of you might be thinking at this point, hold on, I thought this thing was moved left 5. But if we recall some of our chapter 1 stuff, we would know that actually you need to factor this out. You need to turn that 2x plus 5 into 2 by x plus 5 over 2. And that's why we move left 5 over 2, and the domain involves a negative 5 over 2. If we want the equation of the asymptote, it's just the boundary of the domain. So once we've found the domain, it's pretty easy. X equals negative 5 over 2. And lastly, if we want the x-intercept, we sub in 0 for y. Sub 0 for y. So I'll start by just doing that. I'll put in 0 equals negative 2 log base 5 of 2x plus 5. And that is a log equation. We can solve it, and it's not particularly rough. We can move the 1 over to the other side. So we have negative 1 equals negative 2 log base 5 of 2x plus 5. I can divide by negative 2. So at this point, I'll have a half equals log base 5 of 2x plus 5. At this point, I want to get it, I've got my log term isolated. Maybe I'll just rewrite it the other way around so that I can think about bay more easily, okay, or switching forms. There's the base, the answer, the exponent, and I'll start to work that through. So when I put it in log form, I'll get 5 to the 1/2 equals 2x plus 5. Or square root of 5 equals 2x plus 5, because a power of a half is just a square root. Or root 5 minus 5 equals 2x. Or x is root 5 minus 5 all over 2. There's our x-intercept. So for these questions, if you're finding it confusing to find the domain sort of analytically like this, then you can always just make the graph yourself, especially on a test or assignment. If you want to make a graph, be my guest, and that'll help you find the asymptote and the domain. The x-intercepts, you really will have to sub in 0 for y. Sometimes they'll work out to be pretty numbers, sometimes they won't. So that brings us to the practice problems. There are those log graphs that you already did from earlier in the lesson, and they're linked in the video description below. And there are also some questions on page 389 to 390. We could call number 15 a for fun one. If you have time on your hands and you want to do this little investigation, there's some neat things that will happen from it. That marks the end of the video, but if you feel you need a couple more walkthroughs of just doing some graphs, I'll tack those onto the end here. Feel free to tune out if at this point you've got the basic idea. Okay, let's skim through a few. This first one is y equals 2 log base 3 of x. So this is a vertical stretch, x2. That's the only transformation on it. So as a map, it's going to be xy gets turned into x, 2y. What points are we going to apply that to? Always 1, 0, and the base, which in this case is 3, 1. Plug them in. 1 becomes 1, so that's the same. 2 times 0 is 2. The next one we'd have 3, and then 2 times 1. There are 2 points. Nothing has happened with my asymptote, so it's in the same place. So I've got 2 points, and I just connect them up. Okay, let's check out another one. So in this one, we've got an x-axis reflection, and we've also moved right 2. So I'm going to make a map out of that. Right 2 means we add 2 to x. X-axis reflection means our y turns negative. Now what's that going to do to some points? Well, we'll have the key point of 1, 0 and 5, 1, because 5 is the base here. And let's see what happens. 1 plus 2 is 3, negative 0 is 0. 5 plus 2 is 7, and negative 1 is negative 1. All right, we're ready to generate the graph. So the thing I might want to notice here is that right 2 means that the asymptote has moved to the right 2. 1, 2, there's my asymptote. I'm going to make some other points here. So there's the point 3, 0, and there's the point 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, right over here, 7, negative 1. Okay. And then I just connect those points up with a vertical asymptote. And this graph will go down forever. Some people look at it and think it looks exponential, but it goes down forever. It is a logarithmic graph, not an exponential graph. There's no horizontal asymptote. One last one. In this one, we have a vertical stretch by a factor of 3. We are going left 4, and we're going down 1. So as a map, that's going to give us left 4, all right, that's x minus 4. Vertical stretch by a factor of 3 is 3y, and down 1 is minus 1. We're going to apply that to key points. So we have the point 1, 0, and the point 2, 1. Let's see what happens. 1 minus 4, that's negative 3. 3 times 0 is going to be 0, and then minus 1 gives us negative 1. Let's grab another point. 2 minus 4 is negative 2. 3 times 1 is 3, minus 1 is 2. There we go. We've got 2 points, and now we just have to make our axes. And I'm just going to make this so that it'll fit on nicely. So I want to make sure I show that asymptote that has been moved to the left 4 units. It's back here. I've got negative 3, negative 1 as a point. And I've got negative 2, 2. Okay, now that I've got those points, I'm just going to connect them up, making sure I have that vertical asymptote, and continue it on forever. So there we have 3 graphs of logarithmic functions, just going through that technique of making a map and then generating a few points. Could you use other points? Absolutely. but these ones seem to be fairly straightforward. I hope you found this helpful, and good luck with the material.